In this video, we're going to be talking about Quicksort Algorithm, and that's a divide and conquer algorithm. It's used for sorting arrays, for sorting things, and it's an in-place algorithm, means we would be moving stuff in an array. We're not creating new arrays in memory. Divide and conquer part means that we would call the algorithm, the function, again and again for smaller parts of the input. So it would divide the problem in half and then in half and then in half. So, well, not necessarily in half, but it would divide inputs more and more until the problem is solved. So let's start with a little bit of demo with a contrived small mini example of numbers and go quickly over it to see how it works. So this is our input. We have an unsorted array 130, 20, 50, 120. So what happens now is that we need three things in our function, and that would be a pivot, so we would know where the pivot is. And that's the whole idea of Quicksort algorithm. The way it works is that we pick a pivot point and then we sort everything less than a pivot to the left and everything bigger than the pivot to the right. There are ways to pick a pivot, and it's either the first element, the last element, or maybe there are more smarter ways to pick a pivot, like maybe something in the middle. We would pick the first element as a pivot. That would be 100. So now we have this, and that's our pivot. 100 is our pivot, the first element, and we have now two pointers from left that would go one from left to right and the other would go from right to left. At this point, we know that the left pointer shouldn't move because it is the same as the pivot, but the right pointer should move toward the pivot, and each time it moves, it should check if the right element is less than the pivot, because if it is less, we need to swap them. Is 120 less than 100? It's not, so we're going further. Is 50 less than pivot? It is, so we swap them. And now that they're swapped, the pivot also changed, and a pivot points to the 100, but it's now at a different index. So if it was first at index 0, now it is at index 4, and we need to keep track of where the pivot element is at, because we need to know that when we would call recursively the functions to sort everything to the right of the pivot and everything to the left of the pivot. So the idea is pivot finds its way in the algorithm, and when we sort everything to the right and everything to the left the same way. And then after every element found its point, we have nothing left to sort, the algorithm ends. So now our right pointer points to the same element as a pivot point. So what we do is we move the left pointer and check along the way if it is bigger than the pivot. So is 50 bigger than 100? No. Is 30 bigger? No. Is 20 bigger? No. Are marked at green now because the 100 is sorted, and I made it a little bit prematurely because there was one more step where the left pointer would meet the right pointer, and that's the process is called partition. That's where it all ends. Not all, but the first part, the 100 found its point, and now we need to sort everything to the right and everything to the left. But because everything to the right in our small contrived little list example is just one element, we would just leave it in place, consider it sorted, and not only in this demo, it would be considered sorted in the actual code as well. If a part of the array consists only of one element, it's considered sorted. So now we're just looking at the left side, and that would be 50, 30, and 20. It goes the same way. We pick a pivot point, that's 50. We'll look at the right pointer. Is 20 less than 50? It is. We swap them. Now the pivot point's at 50. So now what we have to do is we check at 20, we check 30, they're all in the right place. So this part of the array is already sorted. Next iteration, the pointers, the left and right pointer would meet. And the 50 is sorted. Now we call, there was nothing left on the right side to sort, so we sort only the left side again. And that would be 20 and 30. They're also in the right place. And then we're left only with one element, and that is returned to us as well, and it is sorted. So our array is fully sorted. We have 20, 30, 50, 100, and 120. Now let's take a look at the code. If you understood how the sorted demo works, you might want to give it a try yourself, but if not, or if you already did, you can check out the code that I'm going to write. Okay, what we're going to do here is this. In this code, we're going to need a function swap, and I'm just going to copy and paste it because it doesn't really have anything significant to do with the algorithm. It's just something we're going to need to swap the elements in the array. But let's start writing code. So function quicksort accepts an array. It accepts a start point, which would be default 0. It accepts the end point, which would be the default array length -1. What we start is, as you've seen in the demo, we need pivot, we need a right pointer, and we need left pointer. So the pivot index would be The pivot index would be the start point, the left index would be the start point, and the right index would be the end point. Now what we're going to do, as I mentioned in a demo, we're going from left to right and from right to left until the pointers have met. And that would mean when we're writing code until left doesn't equal right. Now what we check is if array right is less than array at the pivot index. Okay, but if it is, what we do, we swap them. So we call swap, we pass in the array, we pass in the pivot index, and we pass in right, and our pivot index now would point to the right element. We also consider the other case where left is bigger than the array pivot index. So in this case, we would just pass the same thing almost, but just it would be left, and pivot index also would point to the left. What happens here, what we're checking is, if array right is less than pivot, it means it's in the wrong place, because everything on the right should be less than the, everything on the right should be more than the pivot, and everything on the left should be less, and that's what we're checking. And in cases where it's not the case, we swap them, and what we need to do now is we need to make a decision whether to decrement the right or whether to increment the left. The way we do this is if right is bigger than the pivot index, then we decrement it so it moves closer to the pivot index. In other case, when left is less than the pivot index, we need to move it closer to the pivot index with incrementing this. The next part comes the recursion part, and that is if start is less than end, then we call the recursion. Why do we do this? Because we call this quicksort again and again on different parts of the algorithm. First, we start from 0 to the next, to the end, like from 0 to the 6th, if it is the length of our array. Then we would call it from 0 to the 4th, then to 0 to the 3rd. And when they meet, so when this would be, let's say 0 and 0, it got to the point where it has no elements to sort, we don't need now to call the algorithm again and again, because that would call us infinite recursion. And we call now the quicksort 2 times for the right side and for the left side. Quicksort and again, quicksort, we pass it array to both of them. For the left side, we pass the start until the pivot index -1, because pivot index, the element on the pivot index is already sorted. And then we go from pivot index +1 until the end. And we return the array. The other thing I'm doing here is I'm checking at the beginning to double check the recursions won't happen, is if array's length is 1, or if end is less than 0, or if start is more than or equal to the end. Then I just return the array. There might be ways to improve this code. Maybe it looks a little bit ugly. Maybe it can be done a little bit more concise, a little bit more prettier. If you know, or if you found a way to improve this, please share. I am sure there are probably a lot of ways on the internet, a lot of code examples that might be more concise, more prettier. So take a look for yourself if you can improve this a little bit. And the final point is just to test this code. To do that, let's just call console log on the same array that we tested, that we showed in a demo. Let's clear, I already did test it, so now quicksort.js, 20, 30, 50, 100, 120, so it's all sorted. And that was quicksort.